In this problem, we have a tank with air above water. We have a pressure gauge in the air, and we have a pressure gauge at 4 meters below the surface of the water. And then we have this attached to a manometer, which has mercury in it, that is open-ended, and it goes to a pressure of 1 atmosphere at the open end. The height difference between the left and the right sides of the manometer is 26 centimeters, and mercury, of course, has a specific gravity of 13.6. We are supposed to find the absolute pressures, PA and PW of the air and the water, and their gauge positions, answering in terms of torr. So we'll start with finding PA, the pressure in the air, and that is equal to the pressure at point 1 right here. We don't take any rho GH height difference into account because of the small density of air, and we don't know a height difference between where the gauge is and this point anyway, so we assume that the pressure in the whole area is the same. So PA is P1, which we can figure out from 1 atmosphere and then minus this 260 millimeters of mercury. And that will tell us the pressure over here. We know the pressure here is lower than the pressure of 1 atmosphere because the manometer fluid is higher on the left-hand side and lower on the right-hand side. So the result is 760 millimeters of mercury minus 260, which is 500. I have converted, without showing it, from millimeters of mercury to torr. So that's PA, that's the absolute pressure. But the gauge, of course, reads negative pressure because it is relative to 1 atmosphere, so it reads the negative 260. The pressure at the gauge in the water is PA, the pressure of the air above it, plus rho water, G times the height of the water, down to that gauge point. So the second half of this problem becomes primarily a units conversion problem as we translate the rho GH of the water into torr. So we have the density of water at 1,000 kilograms per cubic meter times G times H, and then units conversions. A Pascal is a Newton per meter squared, a Newton is a kilogram meter per second squared, and then 760 torr is 101,325 pascals. So this second part is 294 torr, so we have a total of 794 torr. So the absolute pressure 4 meters below the surface of the water is 794 torr. The gauge then reads 34 torr because it reads the difference between the absolute pressure and atmospheric. Another way to calculate the second part would be to take the height of the water and then multiply that by the ratio between the millimeters of mercury and the millimeters of water that would make the same pressure difference. So that would look like this. We take our 500 torr, that is PA, and we add to it 4 meters of water, and then translate to how many millimeters of mercury that would equate to. And this 13.6 is obviously the specific gravity of mercury. So another way of looking at this is multiplying a height by a ratio of specific gravities, which I will show you here. So the pressure due to a height of water can be equated to the same pressure caused by a height of mercury. And then if we solve this for the height of mercury, we find that you just have the height of the water multiplied by the ratio of the densities of water to mercury, which is the inverse of the specific gravity. So this shows us the pressure in torr due to a height HW of water.